this video, we're going to show how to use the EdgeFirst Studio with the EdgeFirst Profiler on a MacBook M2 Max laptop, which is a 2023 era MacBook using the internal, what's reported as, I guess, a 16 tops NPU. So we've got a few sessions here, YOLO, V5, 8, 11, 26. We'll start with the smallest of the bunch and show how we can hit 800 frames per second on this device. So we've got the sessions here, so showing the YOLO V5 small and nano, and then we've already run a bunch of validation sessions, but I'll run one in real time. So I switch to the profiler. So when you launch it, you get this help screen, and then I'm just going to switch right to the F2 Studio screen, and I'm going to pick the Cocoa detection project. So this is just a terminal user interface. Can run over SSH on any embedded device. Right now it's running on this MacBook laptop. If I pick the YOLO V5 Nano model, and then we've got a generic ONNX float 16 model. So I'm going to run that. When I select it, I can pick the validate option, and then I can run it either on the default ONNX CPU implementation. It's slow, so we don't really do that. And then we've got the 3 CoreML delegates for the CPU, GPU, and NPU. So for this, we'll run the NPU, I hit enter, and then it's going to do a quick load and warm up, and then jump right into the validation. And there we go, we're done running the full Cocoa 5,000 samples, and that took all of 6.6 seconds. Okay, I lied, not exactly 800 frames per second, 714. But there we go. And then if I close out of this, we can tab back into Studio, and we're now just waiting for the analysis job to complete. So what it's done is it's run that full session on the profiler and submitted it to Studio, which now runs a batch job to compare it against the full Cocoa ground truth. So there we go, it's finishing the analysis, and then shortly we should have it ready to inspect. Okay, it was done. So open it up. The first things, we can look at the charts, the results. So we can see for this model, we get 32.9% MAP, which is exactly what we would expect. That's what the full Float 32 model gives. For these models, there's no loss from Float 16. And then we've got all the various validation metrics, and then we also get into the CPU metrics. So this laptop's running a couple other things, so the CPU load is maybe a little bit higher, though I guess not doing much. System versus app is only off by about 10%. We can see our throughput here. Okay, yeah, so it is, well, it varies sometimes up and down, but our mean is 768. But yeah, if we're filtering the P95 and P99, then we see we're in the over 800 FPS range. It's not super flat. If you run this on typical embedded platforms, the deviation's not so high. But anyways, there we go. We get the pipeline breakdown, pre-processing, inference, post-processing time, and then memory usage, which is fairly low for the application, about 180 megs. The delegate, well, everything's running in CoreML, so there's only one layer being measured. and then power usage and whatnot. So the same type of thing you can run on embedded devices. Not all of them let you measure power usage, for example. This Mac does. Other platforms like the NVIDIA Jetson do have these available for measuring as well. Next, we can go look at the actual profiler breakdown and see how we get this type of performance. So the first thing, obviously, when we were looking at those other charts, I glossed over that, but if you were to add them all up, they take longer than would be required for 800 frames per second, which means we're doing all operations within about a little over a millisecond. But the whole application is pipelined, and as we saw when we ran the validation, took 6.6 seconds. So that's 5,000 CoCo images. We're loading the JPEGs off disk, decoding the JPEGs, doing the letterbox resize, normalization, shuffling to channels first, so the NCHW instead of NHWC, loading it into the NPU, running inference, pulling it out of the NPU, doing the box decoding, the NMS, writing the results to a Parquet file so that we can do the ground truth calculation with standard PyCoco tools in that validator app after the fact that we saw. We're also writing a detailed trace file at the same time so that we can review it here, and drawing that nice little text user interface you saw. Interesting tidbit: when first testing this 800 frame per second, the bottleneck was actually that text user interface. It was rendering too quickly. We had to slow that down. Anyways, so this is the full trace profile. So it's pretty dense, even though it's over 6 seconds. But when we zoom in, we can start seeing the breakdown. So the pipelining shows up here. So first thing, JPEG decoding. That's a fairly high overhead. The way we deal with that is we've got it split across 4 frames, or 4 frames, across 4 threads. In each thread is our JPEG decoder is not threaded, so it runs in a single thread. So that splits up well across multiple cores. It is using Neon code, which of course this MacBook is able to run that Neon code. It's an ARM processor, but all the JPEG decoding is happening in parallel and pipelined. We then have the pre-processing. So this is running the same EdgeFirst HAL, our hardware abstraction layer, that runs on embedded devices. It also works on Mac and hopefully soon on Windows as well. We're using Google's Angle library, which is how, while Chrome works on Mac and Windows with its GLES renderer, so it's basically a GLES abstraction layer, supports Metal for Macs and DirectX on Windows. So for us, for the HAL, it means we can run largely the same shaders that we've developed for embedded devices, but we can run them on these platforms. So the pre-processing here runs in about 889, so under a millisecond, 800 microseconds. So that doesn't need to be split up across threads. There's only one GPU, so it would require some more specialized work for that to happen anyways. The actual inference piece is kind of interesting. It looks like it's about half a millisecond, so in theory we could run this even faster if we could, I guess, speed up our pre-processing as well, though we see there's stalls there, and our JPEG decoding. That's really the main bottleneck here, and it's also the main bottleneck on most embedded platforms. When running these smaller nano models, we spend more time decoding JPEGs than actually running inference. And then the decoder happens here. Again, it's very fast, 300 microseconds. The actual ONNX run slots, we run 2 threads for this. So the ONNX model split in half, and we just basically do this ping pong AB, AB, AB. We do the same thing on embedded devices. This works, well, it works really well with, for example, the Era 240 runtime, where we can have this split across 2 or even 4. It shares all the weights and everything. So you've got 4 contexts, but it's the same model memory used across all of them. And it lets us pipeline things and basically hide PCIe transfers to and from the discrete NPU. It works with other things as well, like TF Lite, TensorRT, Halo RT, and whatnot. Which ones work better with it really varies platform to platform. But we see here on this platform that overlap happening. So, one run starting with another one. So, can't quite tell at this level if this is stretching out the NPU time or if there really is room to overlap. We just don't get that level of visibility from the Apple Neural Engine, but we can see here, basically 1.5 milliseconds per run, and they're overlapping, so our throughput is actually able to be higher than that. So this is the type of details we can get through the profiler. We can zoom in more. There's some operations here that are quite a bit smaller. So tensor, allocation, NV to planar. So what NV to planar means here is our JPEG decoder actually exports into the direct NV12, NV16, or NV24 format, depending on subsampling used by the JPEG. So instead of getting an RGB output, we use that NV or YUV output directly, and our shader on the GPU consumes that NV12, 16, 24, or YYV or whatnot. It supports a lot of different formats, and it uses that directly as the operator, including the planar conversion. So that's that from channels last to channels first conversion I mentioned earlier. So all this is all there to see in the profiler. And that's it. That's EdgeFirst Studio with the EdgeFirst Profiler running on a what did I say? A MacBook M2 Pro Max. I'm not sure the exact model, but the 2023 version of the MacBook.